Number 19 on the AMC 12. This one actually has a really clever solution. Okay, we have the roots of this polynomial. What is this ginormous, massive looking sum? Okay, so first things first, we see a cubic. We have to use Vietas, right? So we have that, okay, the roots are a, b, and c, right? We have a plus b plus c is equal to 0 because the coefficient of x squared is 0, right? We have ab, remember we have like negative, like imagine we write x cubed plus 0, x squared plus kx plus 1. We have like negative, positive, negative. That's kind of the way I like to think about this. So ab plus bc plus ac is equal to positive k over 1. That's just k. And then we have abc equals negative 1. That remember negative 1 over 1. That's negative 1. And we're asked to find this ginormous looking sum. What is this, first of all? Okay, let's start back. We can start bashing and trying to figure it out. Let's take a step back here. What does this look like? We have a cubed b squared b cubed c squared c cubed. So it seems like we have, okay, something cubed, some variable cubed, one of our roots cubed, times another one of the roots squared. And it's kind of symmetric, right? You can see it's fully symmetric in all the variables. So we have this cube expression here. These are annoying to deal with, cubes and squares. Let's see if we can figure out something we can rewrite this as, just anything. Let's say a squared b squared plus b squared c squared plus, let's say, I don't know, c squared a squared, right? Let's just pick this one. Why? Because we have cubes. Here we're just do square square, right? And then maybe we have, okay, a squared b squared, and we're trying to get a cubed b squared or a squared b cubed. So we would rewrite this maybe as maybe we should rewrite this as something like, I don't know, we should just try to play around with the expression here, right? Maybe you have a plus b here, right? Or plus so on. I'm just not going to write this thing out, but same thing for bc and ca. We have this kind of expression here. So a squared b squared times a plus b, right? We have, let's just write b squared c squared times b plus c. And then we have a squared c squared times a plus c. That is interesting, right? We have a plus b, b plus c, a plus c. They're all so much like, they're like our sum here, but notice here, this is a really nice condition. We have that the sum is not like, I don't know, it's not k, it's not negative 3, it's 0. And that means that we can substitute a plus b as negative c. And that's kind of the key trick here. A squared b squared negative c plus b squared c squared negative a plus a squared c squared negative b, And then we can just, of course, put the negative here and then just deal with that. Okay, now we have negative of all of this. What is this inside part really? Again, 2, 2, 1, 2, 2, 1, 2, 2, 1. This is actually just, we can actually factor out ABC. We factor out ABC, we get AB plus BC plus AC. That's negative 1. So this is equal to negative 1. And then AB plus BC plus AC, that's K. So this is equal to K. So that's our answer, K. Wow, what a nice solution, right? Like the key trick here is just like, this seems scary. Don't just start brute forcing. Figure out what is this. And especially became nice by this condition, right? So we notice here we have this kind of symmetric pattern. How do we best utilize it? We write it like this. And then we notice the clever minus c substitution, which lets this whole problem unravel apart. I hope you enjoyed this video.